Hi, welcome to the new chapter. So today we are going to start current electricity. So we have done till now what we call static electricity, where the charges actually did not move. The charges stayed stationary, and we were able to find out what is the electric field, what is the electric potential, and the various shapes and sizes. We figured out how to handle all that we did in the static electricity. So now current electricity is about when these charges actually move. They don't stay at the same place, they will actually move. So now what is the meaning of charges moving? Okay. So generally charges move inside a conductor. Okay. It's like, for example, when you say water current, the water moves inside inside a pipe, we call water current. Okay. So like, for example, if you have some pipe in which the water moves. Okay, now if you ask basically what is the amount of water current, we would say total water moved per unit area in unit second, in 1 second, like that. So even in the case of electricity, it is like that. Assume that you actually look at the current that is moving here. So what is the current that is going through this? What is the electric current? If you say, you look at basically charges which move now. So either positive or negative charges, okay, which move here. Okay, now when we talk about movement of charges, okay, it is slightly different in the case of solid and in the case of a liquid, for example. So we have things like solid conductors, okay, and we also have electrolytes. So electrolytes are not solid, they are actually in a liquid, electrolytic conductor. So there are two kinds of conductors we have. In the case of a solid conductor, what happens is that the solid has lots of these atoms inside, nicely packed, and atoms cannot move. They are all stuck to each other, stuck to that their places, and they can only vibrate. Whereas the electrons which are going around those nucleuses, they are, at least some electrons, the outermost shell electrons in the case of metals, are free to move. Okay, they move inside the solid, and such a thing, that is why metals are conductors. The electrons which are at the outermost shell are very loosely bound, and they can actually move inside the conductor. So in the case of metals, where solid conductors, we can say the current actually happens because of the movement of negative charges. It's always because of the movement of negative charges in a solid. Whereas in the case of an electrolytic conductor, which is basically nothing but a liquid, you take, for example, water and put inside water a few drops of HCl, or you can put a little bit of NaCl, sodium chloride. So there will be ions inside the liquid, inside water, and those ions will move. So now when ions are moving, they are not stuck to each other like solid, and only both positive ions and negative ions can move. So the current is now due to both the movements, positive charge movement, negative charge movement. So here actually it is all about by electrons. So main difference, if you see here, it is always through electrons, okay, and it is always because of the negative charges, movement of negative charges. Okay. Whereas this one actually is because of ions, and it is movement of both positive and negative charges. Okay, that's the difference between solid conductor and electrolytic conductor. So we in this chapter going to concentrate only this part. So solid conductors. We will not get into the electrolytic conductors in this chapter, which is basically a kind of chemical effects we will talk about later, or in chemistry also we can study this. So here actually in solids, when we talk about solids, the flow is mostly, the electric current flow is mostly due to electrons. But in either case, whatever the charges that we are basically getting, let's say now charge Q, okay, comes out of this or crosses this place, okay, cross section. In time let us say as a delta q, charge delta q, okay, charge goes through this point in delta t time. So this number delta q by delta t, amount of charge per unit time, is what we call current. So current is simply nothing but charge flow per unit time. That is the definition of current, electric current. And what we do is that may be changing all the time. So it may not be that it is always same amount of Q is flowing. So it may be changing. So to be able to find out exactly how much has changed, how much has flown, you have to take this delta t as less as possible, okay, and find out the instantaneous value of current. So we'll say the current is not just I is equal to the I current itself is a variable which may be changing continuously. So we'll say it's an I of t is simply equal to limit delta t tends to 0 delta q by delta t, which means which simply means basically we are talking about a small interval of time. So in a small interval of time we will measure the stand here and measure the amount of charges that flow and then divide it by. So let's say you want to find out the current of vehicles on the road. You stand there on the road and take your stopwatch and measure in delta t time, let us say 5 minutes, how many vehicles go. Okay. So then divide it by 5. So he will give you per minute how many vehicles. So that is the vehicle current. So similarly here it is the charge current, and that is what we call real electric current. Okay. So electric current is this is the definition. I think you need to basically kind of remember all the time that this is the definition. Whenever we talk about electric current, this is what we mean. We mean charge flow of charges per second and per unit time, and the time that we take is as small as possible, just to avoid changes. And when there is changes, basically you should not be averaging it. You should know the instantaneous value. To get that, you will be actually doing it as small delta t. Okay. Now, so then we actually have studied even in our earlier classes, the previous years, what is basically nothing but Ohm's law. Okay, Ohm's law is a very straightforward law that we discussed about, and we said that suppose if we actually apply current in a particular amount of potential. So what happens is basically if the moment you have a conductor, okay, the conductor actually has internally, okay, the way it works is this. Internally what happens is the conductor will have this nucleus and electrons going around them. Okay. So these electrons, the free electrons, what we call in metals, they are not very tightly bound to the nucleus. So this, if you take a conductor, this is my conductor, there will be so many nucleuses. Okay. Each nucleus has some electrons around it, and I am only interested in the last conduction band electrons, this is what we call. So outermost electrons which are slightly free to move. So what they do is they will be generally moving here like this. So I will basically say that these electrons, okay, I will call this outermost shell electrons like this. These are all outermost electrons like this, and these outermost shell electrons will be continuously moving, okay, in random directions. So this electron, let us say, is moving like this. This electron, let us say, is moving like this. This like this, like this. They are moving in random directions like this. And these electrons, when they are moving in random directions, they also do collide with the stationary nucleus and bond, or they collide with the other electrons and they change their directions, they get back, they change their velocity, all that. So this is happening all the time, and whenever we, even when you have not applied electricity, yeah, but however the moment you kind of apply certain, let us say this is my conductor, okay. So let's say you apply certain electric field on this, okay. the moment you apply electric field on this, or have some kind of a potential difference between these 2 points from here to here, let us say you apply certain potential, you can see that the average of this, okay, will change, in the sense that though these are all moving like this in random directions, if you take the average movement of them, it is 0 when there is no V. Okay. When there is V, the average changes, and hence it starts moving basically in one direction, and on average they still move randomly. Okay. They move in one direction in what we call a drift velocity. Okay, we'll discuss about the drift velocity and what is the velocity of it drifting that side. Like this, it keeps going on one side. So before that, let's understand this Ohm's law tells us that the current that flows, on an average, the amount of Q that passes a certain point, okay, in a given time, we can calculate, and that is the average current. So the average current is actually proportional to this, in the sense when you give V is equal to V is proportional to I, or I is proportional to V. That's how we write it. So we write this as V and I are related like this, or we say, and this is something that we already studied long back, this is called as resistance. So this resistance is nothing but the proportionality constant for these two, voltage and current being proportional. So the potential difference between these 2 points, which we call as voltage, and the current that flows through this, which is nothing but amount of charge per unit time, they are proportional. So this proportionality also tells us a little bit about the nature of R. Okay, what is the nature of R? So we know that the R actually, let us say I have two of this exactly same kind of, assume that I have exactly same kind. I have a conductor which is like this, which actually has, let us say, certain resistance R, which we know is nothing but V by I. Now if I am going to put one, let us say this has a length L, okay, and cross section area, this area is, let us say, A. Now I am going to put one more such block by the side of it, okay, like let's say I'll put it here, attached to this, one more block like this, which has the same length L, okay, and same cross section area, all that. Now we can clearly say here that the current that is flowing here across this, there is voltage V, current is same. Here also voltage V, current is same. There is no difference, both are same. Okay. So in the sense that if you want to calculate together from here to here, okay, you can see that this voltage V and this voltage also V. So these two voltages, actually potentials, generally add up when you connect in series, and hence this potential from here to here is actually difference is 2V. So if you want to find the resistance, which is an effective resistance, is nothing but R effective for this is 2V by I. I is same, which means it is 2R. So we can say that whenever we actually doubled the length, we got the resistance as double the original resistance. So which tells us that the resistance actually is proportional to the length. Resistance is proportional to the length. Similarly, we can figure out that if I actually add, okay, instead of adding this by the side, I am going to add it by this, here parallel. So not add it, actually I will take one of them, just one block like this, and cut this block halfway like this. I will cut it like this halfway. So when I cut this halfway, I have got A by 2 here and A by 2 down, and we can clearly see here the current. Now on an average you can see the number of carriers here and the number of electrons here basically are equal, and you are cutting it into half, the same copper. Okay. So current becomes I by 2. So in this case what happens is that you have current I is equal to I by 2, and you want to find out R now. R will now be equal to R effective will be actually equal to R V by I, which is nothing but V by I by 2 in this case. Okay. So I will write it as I dash actually, that's otherwise it's confusing. So I dash is equal to I by 2, and hence it is 2 into R, 2 into V by I. So that means that I have actually cut it here. Okay. And when I cut it, each individual one, if I take individual one, it has an effective resistance of 2R. Okay. So that means that what did I do? I actually reduced the area by half. When I reduced the area by half, I got an increased resistance by twice. Okay. So it is like an inversely proportional. So R is actually inversely proportional to A. So we write it as actually R is proportional to L by A. R, if you write actually with a proportionality constant, we say R is equal to rho into L by A. And this rho in here is called as resistivity. Of the substance. This is the resistivity of the substance. It is not actually, it does not depend on the length and area. Okay, length and area is nothing but the physical properties of the substance, physical dimensions of the substance. So the total resistance actually depends on the material's resistivity, which is the character of the material itself. Okay, because for copper this resistivity is low. That means resistance is low, it easily conducts. So whereas for some other material the resistivity is high, that means it is hard to conduct. So you can actually see that resistivity gives you an idea of how hard or how easy for the electric current to conduct through that. So now in this case you can see that this rho is actually resistivity of the substance, and which is independent of the A and L, whereas resistance is actually dependent on the nature of the conductor, which is rho, length of the conductor, and the area of cross section of the conductor. So given these values, one can actually easily compute the resistance of a conductor. Now we will now go ahead and look at our original point of basically the drift velocity. We started off talking about how it drifts. Now what I want to figure out is this. So now the resistivity we said is the nature of the conductor. So now the nature of the conductor means what? Does that mean anything about the nature of the atoms here? So the characteristics of these atoms at the micro level, basically how it affects our macro parameter called as resistivity. Okay. So we need to figure that out. Now before going to that, I am going to write down this in a slightly different way, which is, suppose if I am going to write V is equal to IR, okay, and in the sense this is our Ohm's law, and R we have figured out here is rho L by A. Okay. So we have another parameter which we call current density. Okay, current density. And this current density, we actually use that English letter capital J, current density. which is nothing but, as usual, it is density. So divided by, it's not divided by volume in this case, it is divided by the area. Current density is nothing but I by A, because current is flowing like this. And if you are taking a big conductor, there may be more current. We are talking about a cross section area which is unit cross section area. For a unit cross section area, whatever the amount of current is there, that is called as current density. So the current density is that. So we can write down here as I by A is current density J, okay, into rho into L. Now V we know is nothing but E into L. Okay, when you multiply electric field which gets set inside, that into the length is nothing but the E. Now you can actually substitute it here, and we will get this as L gets cancelled, and we get it as E is equal to J into rho. Or if you want to write down, J is equal to 1 by rho into E, which is called as, which is also can be written as J is equal to sigma into E. And the other important part here is that the current is generally used as an average value. Okay, it is basically not given a vector form, whereas the current density is at an instantaneous at that point value. So it is actually given a vector form. So current density, we will write it in terms of a vector, we can write, which is in the same, generally current is in the same direction as the voltage, is E. So I is J is equal to sigma E can be a vector. Vector in the form of Ohm's law. It is called vector form of Ohm's law. So where sigma we call as the reciprocal of resistivity. So you can say if something resists more, then it conducts less. If it conducts more, resists less. So that's how the words are used. So we call this as actually conductivity. Conductivity. So J is equal to sigma E is our physics Ohm's law. In electricity, the Ohm's law, we start with the parameters like V is equal to IR. Okay. Now when you come here in the 12th standard, you are actually getting into the physics notion of Ohm's law, which we talk in terms of current density and electric field and conductivity. So J is equal to sigma E will now onwards be your physics Ohm's law. It is not different from the Ohm's law as electricity we studied, but this is just giving us as a value in terms of those at that position instantaneous values of things, a vector notation. So is J is equal to sigma E. Now what we are going to do is we are going to write here J is equal to sigma E as our Ohm's law, and go ahead and see whether this sigma has any relation to the micro parameters inside the conductor. Okay. So we'll come back to this drift velocity. So when we talked about basically a conductor, we said that it has this nucleus at the middle, and atoms, the electrons are moving around and they are going around in a random fashion. Now let's say that in this scenario, okay, if I say there are n electrons totally, maybe a huge number, 10 to the power of 29, it's okay, n electrons, and every electron, let us say, having a certain velocity, let's say Vi. Vi is the velocity of the ith electron, and I'm okay to keep a vector sum. Vector. Okay. So I want to calculate the average velocity, means we add up all the velocities and divide it by the number. Okay, that is basically called as the average velocity. So what is the average velocity? Let's see what is the average velocity. Average velocity is nothing but 1 by n into sigma Vi for I is equal to 1 to n. This is nothing but, I will call this as Ui, U average. Okay, what is the meaning of U average? U average is nothing but the drift velocity, average drift velocity of all the electrons when there is no electric field applied, in the absence of electric field. In the absence of electric field, in the absence of external electric field, U average must be equal to 0. Means there will be no drift velocity. Okay, U average is equal to 0. So this is our first important relationship, that is, this is basically equal to 0, U average. Now let's apply certain electric field on it. We'll put some electric field E. The moment you apply electric field on it, the electrons will start basically get pushed by the electric field. So when they get pushed by the electric field, what is the force on every electron? Force on every electron is nothing but minus of E into E. Do you agree this? Minus E is its charge. E is the force per unit charge. Okay, E is nothing but electric field. Electric field is the force per unit charge. Into the charge will give you the force. And force divided by mass will give you the acceleration of every electron. So every electron when it accelerates, does it keep on accelerating? No, because the moment it starts accelerating, it goes and basically has a collision, and once the collision happens, it will actually turn back, or it will turn, depending on the angle of collision, it will go in some arbitrary random direction. Okay. So it will now not have, it may be in the opposite of E, then the velocity starts decreasing now. Okay. Then again velocity, when it goes hits something else, the velocity turns back and goes. So the thing is that velocity we can only talk about from the previous collision. Okay. From the previous collision to now, what is the velocity? That we can say. Okay. Assume that the previous collision, at previous collision, okay, there is a certain velocity, okay, which happened at the time at which we basically applied, just one time at which we applied electricity, E. Okay, at that time it had, all the electrons had certain velocity. Okay, I will call that as basically Ui, okay, velocity Ui. So the velocity Vi at a later time, okay, will be equal to Ui plus A into Ti for every electron. For every electron, I am simply using our normal kinematics. Vi is equal to Ui into ATI. Ti is basically nothing but the time elapsed after you applied E, or after the last collision, in both cases. Okay. So now you had Ui. So what was, so if you take for example average for all electrons, average for all electrons, if you take, okay. Now with E, we are talking about now with E. So this is nothing but sigma Vi for I is equal to 1 to n, 1 by n, okay. And this side you have sigma for I is equal to 1 to n, 1 by n, Ui plus A into sigma. A is same because E is same, E is same, M is same. So I is equal to 1 to N, 1 by N into Ti. So let's look at what this is. Okay, this part we will call it as drift velocity with E present. Okay, this is, I will call it as drift velocity Vd average. This is an average drift velocity. Okay, and this one is actually the drift velocity before you applied E. Okay, so in the sense that this value, this whole value before you applied E, we said this average, U average, this is actually 0. This is 0. Plus A is, we have calculated, minus E into E by M. And this whole part inside, what is this? We will see. This is nothing but, okay, the Ti means the, let us say that the Ti, what we are talking about, is the time elapsed, okay, from the one collision till the next collision. That is the maximum it goes to. Okay, next collision, okay, Ti. So when that happens, it again changes. So we cannot use that. So Ti is basically usable only up to the next collision. But the next collision, okay, need not happen all the time at the just after the same amount of time. For every electron, it may be different time. But we can take the average of that. So that average Ti, okay, for all electrons put together, we will call it as basically an average relaxation time, and we use basically a symbol called as tau. Okay. So tau generally we write sometimes like this, sometimes like this, okay, depending on which book. Okay, so I will write tau here. Whenever it relates to time, I write here. Whenever it relates to torque, I write it like this. Okay, tau. Tau is nothing but what in this case? Tau is nothing but average relaxation time. What is this relaxation time? Every electron is just moving and colliding, and after it collides, now before it collides, it kind of relaxes, no collision up to the next one. So the next one, when it collides, the time is over. Again, it starts from fresh. So that is called, one collision to the next collision time is called as relaxation time. So this is the relaxation time. Average relaxation time is tau. So drift velocity is nothing but, now we can write it as drift velocity Vd average, okay, is nothing but minus E into capital E into tau divided by M. So once you get that, okay, why are we doing this? We need this drift velocity to calculate the amount of charge that is flowing. Okay. So the amount of charge that is flowing is how much? Let us see. Okay, if let's say the in one some delta t time, okay, in delta t time, the charge is flowing in delta t time. Basically, that is I want to find out a charge, some charge for some length. Okay, this length and this cross section A. So this length, whatever may be the value of this length, that length will be basically equal to velocity into time. Okay, put some constant velocity, average, on an average. So velocity into time means drift velocity into time, length, and cross section area, let us say, is A. So total volume in this, total volume is nothing but Vt into A. What is volume? Volume is equal to Vd into delta T, some T, into cross section A. That is the total volume. Okay, and if that is the volume, total amount of charge is how much? Let us say if there are n electrons per unit volume. If there are n electrons per unit volume, small n, okay, then you say Q is equal to volume into n into the charge of every electron. So you have this much of volume. Per unit volume you have n charges, n electrons. So total number of electrons is this much. Total number of electrons into charge per electron will give you basically total charge. So this is nothing but Q. So we can actually write it as volume is given as Vd into delta T into A into N into E. This is our Q. So what is our current? Current is nothing but I is equal to Q by delta T, which is nothing but, I will divide this whole thing by delta T. So it is nothing but Vd into A into N into E. We can now substitute Vd. What is Vd? Vd is nothing but minus E. Now this E into E is E square, and A into NE, N into A, okay, these two, and E in the tau into E divided by M. Okay, so the magnitude of current is what we want to actually call as I, in which case we will drop the negative sign and say that this is nothing but NE square into A into tau into E by M. So I am going to basically erase this small part. Now what are we trying to do? Do not lose that idea. So we are trying to basically find out how to relate either conductivity or resistivity to the internal parameters of the conductor. Okay. So now we have got here some relation between I and E. So this I actually will convert into J, because finally if we get it something in terms of J is equal to sigma E, then we can find out what is sigma, that is conductivity. Okay. So I by A is sigma, J is equal to I by A, which is nothing but this divided by A means A gets cancelled, NE square tau by M into E. You can see that this is in the form of J is equal to sigma E, J is equal to sigma E. That is our Ohm's law, J is equal to sigma E. So once you find out that, we can say therefore sigma is equal to NE square by M into tau. You can see how you can show conductivity of a conductor depends on what are the things? The number of charges per unit volume. This is very important. Once you derive it, understanding it is very important. So the number of charges per unit volume, in the sense that the number of conductors, how many electrons are there per unit volume, that will determine. More electrons are there means better conductivity. Better conductivity means lesser resistivity. Okay, lesser resistivity means easily it will conduct. Okay, so resistance will be less. That is N. And E is charge per electron. So it depends on E square. The charge per electron is constant and we don't change it, so that doesn't influence much in our actual calculations. And M is the mass of electron. Those are all the constants. Now you can see the tau. The tau is nothing but the relaxation time. Means how much time something actually drifts without actually hitting the or making another collision. So that is called tau. Okay, so the average of that. Now this tau, it is a function of what? You see here, just because you increase the number of carriers like N, okay, we may not be able to get a better conductivity if that gives rise to more collisions. More collisions means tau will reduce. Okay, so the thing is that when n increases, if tau reduces more or less, it depends on that. If n increases, if tau reduces more, then in fact by increasing the number of carriers, you are actually decreasing the conductivity. Such things can happen. Okay, that is the nature of the conductivity in a conductor. Okay, so now here again one last important assumption we have to understand in this equation is this: when we call this conductivity, we always think that the tau and n are independent of E. So as long as tau and n are independent of E, Ohm's law holds good. Ohm's law is this: J is equal to sigma E. That holds good as long as the tau and n are independent of E. That's because you increase the potential or increase the electric field. If more charges come out and start working, then your Ohm's law doesn't work. So by understanding. So when we get into electronics, we'll see these things happening where Ohm's law fails. So in general, the normal resistors, where conductors, we talk about copper and any other things, this doesn't happen. So there the Ohm's law works. Okay, so this is what is the takeaway. The takeaway is that there is a drift velocity, and the drift velocity is basically calculatable very easily, and you can see that the drifting happens, and that constitutes basically current. Okay, so now using that we can calculate what is the relationship between the drift velocity, or we can say internal number of charges, to sigma, that is conductivity. So we are going to write down those formulae. Okay, so we are going to need them actually. Sigma is equal to ne square by m tau. That is one very important thing we got. And the other thing that we have got is Vd. Vd is equal to E into E, capital E into tau by m. Okay, that is the drift velocity. We will write down that equation too. Maybe of some help for us. Drift velocity to tau by m. So what we are going to do is, we will do one small problem. So that will tell us what is the range of this drift velocity. Is it very fast, very slow? In a copper, for example, what is the drift velocity? How fast the electrons are drifting? So we can figure that out. Okay, and does it basically impact the flow, the speed of the current flow? So we will see that in our next question. So take down this question. The question is, estimate the average drift speed. So we will use the word drift speed also. Okay, well, there is no particular direction to this. Estimate the average drift speed of conduction of electrons in a copper wire of cross section area 1 into 10 to the power of minus 7 meter square. Cross section area is 1 into 10 power minus 7 meter square. Carrying a current of 1.5 amps. Carrying a current of 1.5 amps. Assume that each copper atom contributes roughly 1 conduction electron. So every copper atom gives 1 electron. So let us just assume, he is saying that just take this as an assumption, okay, for this question. The density of the copper is 9 into 10 to the power of 3 kgs. Okay, so density of copper is 9 into 10 to the power of 3 kg per meter cube. So what are we to find out? And also its atomic mass is equal to 63.5 atomic mass units. So, point A is to find out the V drift velocity or drift speed. Point B is compare the drift speed obtained above with the thermal speeds of copper atoms. Point B is basically compare this with the thermal speed of copper atoms. Thermal speed. Very interesting. This thermal speed means what? The copper atoms are actually vibrating. And what is the speed with which they are vibrating? On average. Find that out. And thirdly, speed of propagation of electric field. So what is the speed of propagation of electric field? Speed of electric field. So you will not be able to quickly do these things, mainly because these are not something which are known to you immediately. So this problem will help you to understand that. So first thing that we will do is the A part. Okay, drift velocity, there is a formula that is there. Drift velocity Vd is equal to E into capital E into tau divided by m. That is the drift velocity. Okay, but there is also another way of looking at drift velocity, which is nothing but from the current you can come back to drift velocity. So current is what? I is equal to, we said that I is equal to drift velocity into basically the delta t into drift velocity into n into E into A, correct. This is what we said. Number of drift velocity into Vd is equal to Vd into n into E. So current actually is equal to, you can see, nothing but drift velocity into number of electrons per unit volume into the charge into A. That is our velocity. Okay, that is our current. Now, if we don't have A, then it will get current density. Okay, this is the current. So how do we now calculate these values? So we want to calculate Vd. So Vd is simply now equal to I divided by n into E into A. So Vd is equal to also I into n I divided by n into E into A. What are the things we know in this? We know E 1.6 and we know A is also given. So we can write here 1.5 divided by n is not known yet. Okay, let us say E is 1.6 into 10 power minus 19 and A is 1 into 10 power minus 7. This we know. Okay, what is n? How do we find out n? Number of electrons per unit volume. Number of atoms per unit volume is same as number of electrons because one atom has one electron. The number of atoms per unit volume. How do you figure that out? So let's say that you have about they have given us the density. Okay, so from there we can go. So 63.5 grams basically would give you how many molecules, how many atoms? Avogadro number 6. Let us say 6 into 10 power 23. Okay, so in one volume, how much do we have? We have 9 into. They have given us basically density of copper. So that into basically 10 power 3. If you multiply that, you will actually get the number of electrons per unit volume. Okay, number of atoms per unit volume, but it is same as number of electrons per unit volume. So this would be actually equal to N. So how much is this? This will turn out to be, basically, let me just tell you what I get. Comes to 8.5 into 10 power 28 per meter cube. If you substitute into this here, you get Vd, if you calculate, as something like 1.1 into 10 power minus 3 meter per second, or we can say 1.1 millimeters per second. And you will be surprised to see the drift velocity is so very small. It's very, very small drift velocity. So just 1.1 millimeter per second, it is drifting like this. So does that mean that it actually current takes so much time from, in one big conductor, takes so much time to reach that side? No, because of the C part, the speed of electric field, which we are going to study later in the electromagnetic theory. So speed of electric field is like speed of light. There's a moment you set up an electric field. The electric field is set up on the whole conductor everywhere. So there may be drifting current here and there is a drifting current there. So there may be electrons drifting here, everywhere they are drifting. It is not that this drift will cause the other drift. The electric field will cause the other drift. So the moment the electric field is set up, the drifting starts immediately. That means it's almost the speed of electric current, what you can say, is almost same as the speed of light. Okay, so slight difference, maybe, that's all. So that is basically the third question. What about the second part, that thermal? The thermal speed comes from, actually, interesting thing is that if you can actually take each copper and vibrating, and that will give rise to temperature. Now you studied that in the last year. Okay, you say that the energy half mv square, the average of that energy, will be actually nothing but 3 by 2 kb into T. I studied in the last year. Okay, so the kb is nothing but Boltzmann constant. So the value of the Boltzmann constant is like 1.38 into 10 power minus 23. Okay, kb is 1.38 into 10 power minus 23. And T, let us say, is the room temperature, 300 K. If you take these values and you take the mass of one of the atoms is like 63.5. Okay, the mass m, I will take it as first, the 63.5 is actually grams. 63.5 grams of a particular of copper will give rise to this many molecules, Avogadro number of molecules. So per molecule, how much it is? That is 63.5 divided by Avogadro number. Avogadro number, let us say 16 10 power 23. This many grams. So into 10 power minus 3 kgs. So if you substitute these values into this, okay, the V value you will get as square root of, basically V is nothing but square root of kb 3 kb into T by m, which is nothing but, for if you substitute all these values, will come to somewhere around 3.4 into 10 power 2 meter per second square, meter per second. So that means it's vibrating at a very, very, very high speed of, let us say, 300 meters, 340 like meters per second, whereas the electron drift velocity is very small, 1.1 millimeters per second. So drift velocity is very small when compared to even the vibration of the copper atoms. Just to get an idea of how it is, and the electric field speed is as much as velocity of light. So all these things are involved in the conduction of electric current in a conductor. So we'll give an idea of what it is. So last part is what we call one more new term. So we learned the term of, we learned quite a bit of terms actually. In fact, we learned actually relaxation time, drift velocity, resistivity, conductivity. So many terms we learned today. So we're going to now learn just one more term, the last one. But all these terms are related. They are not really new terms, and they are also intuitive. If you see resistivity, means it gives rise to resistance. Conductivity will be opposite of resistance. So this is easy to remember. It's not like hard. Okay. So the next term basically I want to introduce is something called as mobility. Okay, the carriers, the charge carriers like electrons. See, these are the things that are going to be very, very useful when you get into electronics, because we talk about mobility of the charges and even electrolytic conductor, mobility, how fast they move. So mobility is a very important term. So what is mobility? Mobility, we define it as nothing but mobility is defined as per drift velocity. Drift velocity we know. Drift velocity maybe is dependent on the field that you have set up. More field, more velocity. But per unit field value E, how much is the velocity? That is its mobility. Okay. So let's say mobility is drift velocity per unit field strength. E. That means mobility mu, mobility is given by the symbol mu, is nothing but you take the Vd, that is basically a magnitude of that, divided by E. So unit E, if you give, what is the drift velocity, how much it drifts, that is the nature of the carrier that moves. Okay. That is the mobility. For electron mobility, we can calculate what is the value. For every kind of a charge carrier, different kind of value for mobility will be there. Okay. So for Vd, you can write it as E tau by m into E. This E cancels, E tau by m. And you can see that mobility simply depends on these characters. Very interesting thing. Okay, you can see the mobility simply depends on what is the charge and what is the mass, what is the relaxation time. That means that it is very nicely mobile if the relaxation time is high, means if it is not hitting anything. So that is the environment. The environment variable is this, whereas E and M are specific to that carrier, charge and mass. So this is called mobility. So after having seen these things, the next step that we are going to do is to understand basically what is the limitations of the Ohm's law. So what happens if in which scenarios Ohm's law has limitations. Then we will also look at the resistivity itself, the rho, what we talk about, our conductivity sigma. How does it vary with temperature? So these are the things we will do in the next session. Thank you.